record to the cloud. Okay, now it should be recording. Hi there. Okay, so welcome to the second workshop. This one's going to be a little less formal than the previous one, so I don't have slides prepared. I just have my whiteboard, and we're going to go over concepts that you guys are interested in. It helps to have a little bit of audience participation. So let's just go around. I'm going to have each one of you sort of introduce yourself, give your name, give your major, and then what inspired you to get started with the Quantum Hackathon. Try to keep it brief, but if you take a little bit of time, that's fine. So I'll call people out in the order I see them on the screen. So Hung, you're up first.
Hey everyone, my name is Hung, and the reason why I joined this hackathon was just because I'm just a bit curious about quantum physics in general. I have never taken any sort of quantum physics before, so I just want to try something.
Good reason. All right. Oh yeah, go ahead.
No, that's it.
Cool. Jenny, name, major, why you're interested in quantum.
My name is Jenny and I'm a computer science major. I plan on doing quantum computing related research next semester, and I'm just generally interested in quantum, so that's why I'm here.
Nice, cool. Jordy, you're up next.
My name is Jordy. I'm a CS student as well. I missed out on the quantum summer school this summer. So I was like, oh, I want to just do a quantum challenge, whatever it might be. So I learned about the fall challenge a long time ago, but then I ran into this fall fest. I was like, this is my chance. Yeah.
That's a good reason. Now that summer school, in case some of you don't know about it, IBM runs the Qiskit Summer Learning School. You should definitely sign up for next summer if you're interested. I think it's what, 2 weeks, 3 weeks? And yeah, it's got some big names talking and they walk you through a bunch. Next on the list is Rifat, and correct me if I'm not pronouncing that right, but go ahead, name, major, why you got interested.
Yes, sir. So you guys can hear me?
Yep, we can hear you just fine.
All right, so major in computer science, and the reason I joined is so I can learn more about quantum computing, because it's always interested me how fast it processes everything. So it's something that I really think is going to be involved a lot in the future of technology.
Sounds good. All right. Thank you so much.
Good.
Yeah. Next up on the list is Shashank Iswara.
Hello, I'm Shashank. I'm a CS student. And I guess I'm really curious about like quantum computing and how that works. That's why I joined the hackathon and want to learn more.
Very good. And next on the list is Shreya Naka.
Hi, my name's Shreya. I'm a CS major, and I found quantum computing really interesting, and that's why I want to learn more about it. And yeah.
Sounds good. And then Songsen Chen.
Yeah, hi, my name's Songson, and I'm also a computer science major, and I'm just interested in quantum computing because it's just fast.
Cool. All right. So let's get started. All right. So I'm gonna share screen. I'm gonna share a whiteboard. Okay. So last time, the first workshop, Will went over a bunch of different topics. Some of the topics he covered were entanglement. He covered superposition. I hope my writing is legible. Superposition. He covered, I hope he covered interference. I'm not sure. I haven't watched the recording yet. And then what were the other topics that he covered again? It was, there were 2 more. Do you guys remember? Anyone who attended?
Qubits.
Okay, qubits, yeah, probably qubits. I don't know if he went into gates. Do you guys remember if he went into gates? Probably not.
I think we went over a little bit of gates, not much.
Okay. So are any of these topics, are these topics that you guys want clarification on? So I'm here as a sort of reference where I'll re-explain a concept a little more interactively if you guys want me to. So
can we just
anybody
go over interference?
Absolutely. Let's go over interference. Okay. So I'm assuming that you guys understand entanglement and superposition a little bit. So interference, every single quantum state. Let's first start off with a quantum state. So this is called Dirac notation. All this is saying is that this here is a vector. This is called a ket. The other version would be called a bra. And so a ket would correspond to a vertical vector, a column vector, and a bra would correspond to a row vector, like this. So whenever we have a quantum state, we often represent it as the sum of multiple different basis states. And basis states, you can think of them as classical bit strings. So for example, this state here, this is actually a terrible one because there's 3 in it. Let's make this a little bit easier for everyone to understand. So let's make this a vertical column vector. And let's say it's got A and B. So this is, for example, you could think of this as the coordinate A comma B in the 2-dimensional XY plane, where it's like A units this way, B units this way. That's what this vector represents, right? And so another way to write this is as A times the 0 basis vector plus B times the 1 basis vector, okay? So this is just me covering superposition. This is probably something you may have seen before. If you haven't seen it before, all it is it's a different notation for writing out vectors. You can think of this as like the X coordinate and this as the Y coordinate. And so, so this is what superposition looks like. Interference is something that's unique to quantum computing, and it's unique to quantum computing because these numbers here can be negative, and negatives and positives can cancel out. So what do these 2 numbers mean? I think Will probably didn't cover this. There's something called the Born rule. This is probably one of the most important rules for quantum computing. So the Born rule, what it says is that whenever you have a state like psi, which is A0 plus B1, if you try to measure psi in the 0-1 basis, if you take, it's like if you open the box and look at Schrodinger's cat, what happens is the superposition collapses. So you won't see psi, you'll only see 0 or you'll see 1. But those 2 events happen with different probabilities. The probability of seeing a 0, so the probability that you see a 0 is the magnitude of A squared, and the probability that you see a 1 is the magnitude of B squared. Why did I say the magnitude instead of just squaring explicitly? It's because A and B can be complex numbers. That is, they can be things of the form alpha plus beta I, right? And so in that case, in order to get the magnitude, you have to take the absolute value. But we don't really need to worry about that. All we really care about for quantum computing is that there are positives and negatives. There's a proof, and I'm of course not going to prove it here, but there's a proof that you can simulate any quantum computer using complex values with one that only uses real values. So for the purposes of what you're likely to do, you won't really need to mess around with complex values too much, though it is helpful to understand them if you'd like to go deeper into it. Okay, so the Born rule says that things happen with these probabilities. Now, if you had, let me try and come up with an example where addition would happen that cancels things out. Come up with a clear example. All right, this is not a clear example, but it's what we're going to use for now. So if you had a state where it was A plus B I. Oh, sorry, why am I saying I? It's a 1. That's a 1. I want it to be so that things cancel out. Let me just give me a second to think about it to come up with one that's better than this. Okay. Because I don't want to say one that's confusing by just adding together 2 vectors. I really want it to naturally come out of things, but I'm afraid to introduce the Hadamard. How many people here, by show of hands, are familiar with the Hadamard gate? Let me open up the participant so I can see. Just raise your hands on Zoom and let me know if you've seen the Hadamard gate before. Okay. So I'm seeing 3, 4 hands. Songsen is also raising his hand. Nice to see you. Okay, so 4 hands. It seems a couple people are not familiar with the Hadamard gate. Okay, so before we go off onto a tangent and help explain this, I'm going to try to close this discussion on interference and say interference is when you have like A0 and then somewhere else you have negative A0, and then you add these two amplitudes together and you end up getting 0 times 0. So this whole thing just vanishes, it's just gone. So what that might look like in an experiment, for example, if you're measuring light waves hitting a screen, you might have the classic example is a double slit experiment. The light waves are coming out here, the light waves are coming out here, and you have constructive and destructive interference, kind of like ripples on a pond, where when 2 waves over here, when they're both at high points, then they add together. And when one of them is at a high point and the other is at a low point, then they cancel out. And so you end up, so I don't know if you guys have seen this, the light is coming in through these 2 slits here, and then this is a wall. And then if you looked at the wall, you actually just like, this is a different view of the wall, the front view of the wall, you'd see these like lines coming in where it's like bolder in the center and it sort of fades out going away from the center. So it's just like single discrete lines. Sorry, this one's really messy, but they sort of go out from the center, and that's from constructive and destructive interference. This is actually, interference is the main reason that quantum computers have any advantage over classical computers, because interference is what gives them the power to amplify some probabilities and destroy other probabilities in order to make your desired measurement results be the most likely thing for you to measure. Okay, so that sort of explains interference, though I wanted to give a more concrete example. Are there any questions on what I've said so far? And don't be afraid to ask something completely. You can ask me about like adding integers and I'll help you out. Like, don't worry about it. Is there anything, any questions? Any part of this that didn't seem clear? All right, moving onwards. So I'll explain the Hadamard gate, and hopefully I'll be able to use it to come up with a good example of interference taking place. So I'm going to go to a new slide. So the Hadamard gate, for those of you who haven't seen it. So first of all, let's explain how quantum gates work and how quantum circuits work. So in classical computing, you might have seen gates like this and gates like this. Hold up just a second. I need to turn my video off because my roommate is taking a shower right there and needs to walk out behind me. Okay, sorry about that. Video off here. All right, you can come on out. My apologies for that. All right, sometimes you gotta live with roommates. All right, so here's, you might have seen these gates before. So this is the OR gate, this is the AND gate, and this is the NOT gate. And so each of these, if you put in A, B, you'll get A or B. If you put in A, B, you'll get A and B. If you put in A, you'll get not A. So you've probably seen these before if you're in computer science. These are just logic gates. They do exactly what you'd think they do. They take in single bits and they output single bits. In quantum computing, we have gates that are similar, but there's a fun feature of quantum mechanics is that information is conserved. So everything has to be reversible. All computations have to be reversible. So an example of a computation that's not reversible is AND. If we draw out the truth table for AND, it might look something like this. So here's A, here's B. And then here's going to be the output, A and B. So let's get some audience participation. What's 0 and 0? Just shout it out.
0,
0, thank you. What's 0 and 1?
0.
0, very nice. All right, somebody else. What's 0 and 1? What's 1 and 0? Give me the next two, whoever shouts out next.
0 and 1.
Yeah, okay, great. You're all awake. So this is an AND gate. Now, the reason this isn't reversible is, say I hand you a 0. I say A and B equals 0. Can you tell me what A and B were? You can't. So that's what makes this not reversible. It could be any of these three options. You don't know. So there are ways to make the AND gate reversible. The way that quantum computing gets around this is that they define something called a Toffoli gate, which I can go over if you guys are interested. But first of all, let's explain what a quantum gate looks like. So a quantum gate, here's a couple common quantum gates. One that's really nice. Is it the Z or is it the X? Give me a second. I'm pretty sure it's the X gate. Yeah, it's the X gate. So this is equivalent to the NOT gate because the NOT gate is reversible. And so what this looks like as a matrix, and I'll explain this in a second, is it looks like this. And I always switch the Z in the NOT gate. So give me a second just to double check that I'm not telling you something wrong. This is just me. It's not that. Yes, I got it right. Okay, cool. Just wanted to make sure. So yeah, this is the X gate. It looks like this. So if you remember from the previous slide, I told you that 0 is like your X coordinate and 1 is like your Y coordinate when you're adding together single qubit states. So this in vector form would look like this. And this in vector form would look like this. And what this is saying is it's 1 unit in the X direction and 0 units in the Y direction. This one is 0 units in the X direction and 1 unit in the Y direction. Okay, so if you imagine graphing them out, this would be the 0 state and this would be the 1 state. Okay, so what this matrix here does is that if you multiplied by 0, for instance, can anyone tell me what this would become? Just doing matrix multiplication, as you know.
0, 1, 0 on the top.
0. Yep, that's correct, which is the 1 state. So the way you'd write this out is you'd say X, because this is the X gate, X times 0 equals 1. Similarly, can you tell me what X times 1 is? Somebody else? Let's see how many people are paying attention. Anybody? Bueller?
1 0.
1 0. There we go. All right, cool. So it becomes 0, which is 1 0. Okay, so cool. This is the NOT gate because it takes 0 to 1, it negates 0, and it negates 1. Okay, so now let's take a look at the Hadamard gate. This is a uniquely quantum gate. It doesn't really work out with classical bits. The NOT gate clearly is also a classical gate, but Hadamard is special. So what does this gate look like in quantum form? It looks like this. Okay, so this might look a little bit cryptic. What is this 1 over square root of 2 doing in front? Okay, so every single quantum gate has to satisfy a couple of properties. So it has to be reversible. And it has to take norm 1 vectors to norm 1 vectors. This is called its norm preserving. Okay. So you may or may not have seen this, but when you have a quantum state, like psi equals A0 plus B1, these states need to be normalized. What that means is that norm is like magnitude. You could think of it like the size of the vector. And so what it means is that when you add together a squared plus b squared, you get 1. Okay, it's a unit length vector. That's the way to think about it. And the reason for this is that a squared, this is the probability of measuring 0, and this is the probability of measuring 1, and probabilities need to add to 1. So all quantum states are normalized in quantum computing. We try to keep them normalized. So every single quantum gate, it takes in a quantum state and it outputs a quantum state. And because of the rules of quantum mechanics, it has to be reversible. And because probabilities need to add to 1, it has to be norm preserving. Now, the only matrices that satisfy these properties are called unitaries, or unitary matrices. Okay. So unitary matrices, the way to think about it is that every single column in the matrix is a unit vector, and all of these columns are orthogonal to each other. Okay. You don't really need to fully comprehend what that means, but you can take a look at the X gate, for instance, and these two are both norm 1 vectors, and they're orthogonal to each other. If you graph them, they're at 90 degrees. Okay, so every unitary is a quantum gate, and every quantum gate is a unitary. That's a good thing to know. So when we write out quantum circuits, they look a lot like this. So there's lots of lines. Each one of these lines is like a single qubit. This could be state 1, this could be state 2, this could be state 3, and state 4. And then the computation goes from left to right. And then you have gates along these wires. So that would be a Hadamard. You could do an X gate over here. There are also multi-qubit gates. So those might look like a big block that goes over two different wires. And one particular 2-qubit gate that's extremely useful is something called the C0. And we draw that like this. So like on its own, it would look like a plus sign inside a circle and a dot. The dot is called the control. And this is called the target. Okay. Before I move forward, I'm kind of just going through a whole bunch of things. I'm making my way back to the Hadamard eventually. Are there any questions on what I've said so far? Anything? I'm sure there's like some curiosity.
So what is that empty square next to the X to the right of it? So
Oh, this thing here?
Two of them?
Yeah. So if I wasn't so lazy, I would have made it so that the real way it should be drawn is like they're going through the gates, right? And then this would be what it's saying is that it's taking in 2 qubits here. It's taking in 2 qubits and it's outputting 2 qubits. So this you could imagine, for example, this AND gate over here, instead of having a single output, it could output 2 things. So for example, you could have A, B, this one outputs A and B, and this one outputs, I don't know, let's make it output A, okay? Would this be a reversible circuit? No, it would not be reversible. But anyway, so this is kind of what it would look like classically if you had a gate that takes in 2 inputs and 2 outputs. This is the same exact thing. It's taking in 2 qubits, it's outputting 2 qubits. I haven't specified what it is. It could be all sorts of things. Let me try and think of a 2-qubit gate. Nothing comes to mind. The C0 is the most common one. Let's see if the internet has one for me. Oh, there's controlled Z. I guess there's a swap gate. Let's do a controlled Z. I've lost it. There you go. So, or we could even just write C0. And these 2 gates would be the same gate. It's just another way of representing it. C0 is short for controlled not. And you'll see why in 5 seconds. Right. So controlled not. I'm going to tell you what it does, and then I'm going to ask you guys to construct the matrix of controlled knot on your own. So just by a raise of hands, how many people know the matrix of controlled knot or have seen the matrix before? Or actually, how many people haven't seen it? Raise your hands if you haven't seen it. And don't worry, you can't see hands in the recording. So if you raise hands, no one's gonna know. Okay, cool, cool. Anyone else? Anyone else hasn't seen it? All right, cool. All right, so there's still some interest. I'm not explaining things that people already know. That's good. Okay, so I saw 3 hands there who haven't seen it before. I want you 3 hands. I want you to participate in this next section. You're gonna figure out this matrix on your own, okay? So what controlled knot does is it takes in an input bit. So here's a controlled knot for you. Takes in 2 bits. And if the control bit is a 1, then it flips the other bit, okay? So if the control bit is a 1, it flips the other bit. So here's a truth table. So here's A, here's B, and here's gonna be, we'll call it X, and we'll call it Y. Okay, so here's A, B, 0, 0, 1, 1, 0, 1, 0, 1. And the outputs are going to be X and Y. So first of all, let's do X. Does this gate do anything to this bit on the starting wire? Any of you 3 who raised your hand? No, I'm seeing Rifat say no, and that's correct. That's correct. It doesn't change this bit. Now, what does it do to the other bit? Can somebody tell me what the 4 numbers here will be?
0, 0, 1. 0, 0, 0, 1.
0, 0, 0, 1.
Yeah, I think.
Not quite. So what it does is if A is 1, it flips B. So 0 is correct. A is 0, so it doesn't flip B, it leaves B alone. What would happen when A is 0 and B is 1? Should it flip B? No. So it's going to remain 1. That's correct. All right, how about this next one? So A is 1. So what does that mean B is going to become? It's going to become what? Someone said it, I didn't hear it. 0? No, not quite. So B is, it's going to become 1. It's going to become 1. So B here was 0 and A here was 1. This says if A is 1, you flip B. So if A is 1, you're going to flip B. So B is currently 0, so you're going to flip it to be 1. Over here, B, if this was 0 and this was 1, then this guy, oh, it's 1. So it flips B and this guy's going to become 1. Cool. All right, and then the last one. Can anybody tell me what the last bit in this truth table is going to be?
0.
0. Good job. Nice. Okay. So this is the truth table for this matrix classically. Now, the fun thing is if you can write a truth table for a circuit that tells you where to take every single classical input, then you can create the matrix that defines this quantum gate. And the reason for this is that the classical bit strings are a basis for the quantum space. If you aren't familiar with linear algebra, you might not know what a basis is. It's just like the coordinates you're using, like X and Y. Okay, so, right, we want to define the matrix for this. So this is a 2-qubit gate. So this is going to be a little bit challenging, but I'm going to tell you that every single 2-qubit state comes in this form. So here is psi, that's a 2-qubit state. It comes in the form A 0, 0 plus B 0, 1 plus C 1, 0. Sorry, I'm running off my screen here. 1, 0. Nice to see you, Hung. Thank you for coming. Yep, and I hope you'll come to the other workshops. All right. Yeah, so every 2-qubit state comes in this form. And what this is saying is it's a superposition of all the possible classical outputs. It's a superposition of the 4 possible bit strings that you could get. Okay. And so the way to represent this as a matrix, you would write this out as A, B, C, and D. And the way to visualize this is kind of hard. It would be like a 4-dimensional vector, right? So you go in the X axis, the Y axis, the Z axis, and then also some 4th axis as well. And you go A units in the X, B units in the Y, C units in the Z, and then D units in the, I don't know, Z2, whatever the 4th axis is. Okay, so that's this vector here. Now we want a matrix that will take 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, and 1, 1 to 1, 0. So let me open a new slide. I'm going to rewrite the truth table, and then we're going to figure out the matrix of C0 together, okay? So we had A, B, X, Y, boom, boom. I should have made this C and T, or T and C for C and T for control and target. That's on me. But since you guys probably gotten comfortable with these, I'm going to continue using the same letters, even though it would have been better to choose different ones. Okay, 1, 1, and 1, 0. Okay, so writing this out in vector form, 0, 0 is the so I'll write out psi again so you guys can see that. A 0, 0 plus B 0, 1 plus, let me move this so I can actually write at the top of the screen. C 1, 0 plus, oh wow, that was really ugly, plus D 1, 1. And this can be written in vector form as A, B, C, D. Okay, so 0, 0. Can anybody tell me what this is in vector form? Just shout it out.
1, 0, 1, 0.
Close, close. So what's A here? A is going to be 1. And then what is B going to be? I'll actually just do this one so you guys see the first example because it might not be clear what's going on. A is going to be 1, B is going to be 0, C is going to be 0, and D is going to be 0 because 0, 0 is just this. It's this right here, and it's not these guys. It's none of these guys. So this vector is just going to be 1, 0, 0, 0. Similarly, 0, 1. Now let's try an example where you guys, you've seen 1. Maybe you can extrapolate. What's 0, 1 going to be?
0, 1,
Vector form.
0.
Yeah, 0, 1, 0, 0. That's correct. So let me write that out. 0, 1, 0, 0. And then can anybody tell me what the next 2 are going to be?
0, 0, 1, 0, and 0, 0, 0, 1.
Thank you. Perfect. Okay. So we've got, and again, these are basis vectors. So you can imagine this is 1 unit in the X direction, 0 units in the other directions, 1 unit in the Y direction, 0 units in the other, and so on. Okay. So we just said 0, 0 gets taken to 0, 0. So we want some matrix here. This is going to be the C0 matrix. It's going to be a 4 by 4 matrix. And it's going to be 4 by 4 because it takes in a 2-qubit state, which has vectors. They're 4 vectors, 4-dimensional vectors. It takes in a 2-qubit state and it outputs a 2-qubit state. Okay. So yeah, so we want it so that when you put in 1, 0, 0, 0, we want it to output 1, 0, 0, 0. Now, I don't know if you guys are familiar with linear algebra. Can any of you guys tell me any of the entries of this matrix based on the fact that when it multiplies by 1, 0, 0, 0, it needs to be 1, 0, 0, 0? Can anybody tell me what any entries in the matrix?
The diagonals are all 1.
The diagonals are all 1. Not quite. You're close.
Is it 1, 0, 0, 1?
1, 0, 0, 1 along the diagonal? Is that what you're saying?
Oh yeah.
0, 1 along the diagonal. Not quite. The diagonal isn't really what I'm going for here. I'm actually going for the first column. Can anyone tell me what the first column of the matrix is?
1 0 0 0.
That's correct. It's 1 0 0 0. And the reason for this, I don't know if maybe some of you haven't seen matrix multiplication before. If you haven't, if you had like A, B, C, D, and you had so this is just like a 2-dimensional 2x2 matrix and a 2 vector. The way you'd multiply it, the way I like to imagine it is I like to imagine you put the matrices like this so that the corners touch. Okay. And then this entry here is, so I shouldn't write a 0 because that looks like a 0. It's like you multiply downwards. You sort of like match the two together, right? And so this is going to be XA plus BY, or I should have said YB, but whatever. And then this one's going to be XC plus YD. And so this is just a 2 vector again. So it's you multiply and then you add all of the things together. So here, so that's just normal matrix multiplication. Here, when you multiply this column vector, what it's going to do is it's going to multiply everything by 0 except the first column. The first column is going to get multiplied by 1. And so this 1 here basically just selects this first column. It just writes it out. And then all of these guys are going to multiply the other columns by 0, and they're going to just disappear. So we got that the first column is 1 0 0 0. Now, can anyone tell me what the second column is going to be? And to help you out, I'll just write out where it's supposed to go. So we have that 0 1 needs to go to 0 1. Can anyone tell me what the second column is?
0 1 0 0.
Okay, perfect. Now let's go to the third column. This one might trip you up because it's not going directly to itself. It's going to a different vector. So this one takes this vector. It takes 1 0, and it takes 1 0 to 1 1, right? So instead of taking this vector to itself, sorry, I need to erase this 0 here. It's going to take it to 1 1. This is 1 1 right here. This is 1 1. Sorry, 1 1, and this guy here is 1 0. So it takes 1 0, goes to 1 1. So what is this vector here going to be? This column vector?
0 0 1 0.
Not quite. Close.
0 0 0 1.
Yeah. 0 0 0 1. And then can anyone guess what the final vector is going to be?
0 0 1 0.
0 0 1 0. And this is because it takes it takes 0 0 0 1 to 0 0 1 0. So this thing is going to be the last column. So this here, this matrix we just drew out, 1 1 1 1 with zeros everywhere else. This matrix here is the matrix that represents C naught. This is C naught. Okay, so that might have been a little deep in the weeds. We went far into linear algebra. Are there any questions about what we did so far? Anybody asking themselves, what's the point of all this? Why are we doing this? What's wrong with you writing 1s and 0s like this? Anybody asking questions? I won't be offended. Go ahead, ask. I can't really quite hear you. Could you? I don't know.
He's asking, what are we going to use? Like, not what we're going to use this for, but what is quantum computing usually used for in like relation to work and applications?
Okay, yeah, that's good. Yeah, so all of this that I've been explaining so far was just gates. Let's answer that big general question. And by the way, you guys are going to end up using these gates a lot when you code things in Qiskit. So I wanted to go a little deeper into the math so you guys understand them. If you have any questions about the gates while you're working, you're welcome to email or message me on Discord. Okay, so let's answer that big general question. That's a fun one. Okay, so what is quantum computing useful for? Let's poll the room. Does anybody have any things they've heard quantum computing is useful for? I have a couple I could think of, but Anything you've
I
heard in the
assume
news?
it's faster than regular classical computing.
Okay, so this is a common thing that they say. They say it's faster than classical. So this is sort of true. It's not exactly true. It's faster than classical sometimes. So there's specific use cases where quantum computing might be helpful. It's not like it's going to make every single thing faster. It's very unlikely that we're going to be replacing classical computers entirely with quantum computers. Classical computers have their use case. They're useful for a lot of things, and quantum computers have other use cases, things, specific problems that they're better at. So what specific problems? One candidate is physical simulation. This is a really common goal of quantum computing. What this means is simulating physics, because we live in a quantum world where quantum physics governs the way everything works. And so classical machines can't keep up with quantum computing. And the reason for this is, you may have just seen this. We had a 2-qubit state. A 2-qubit state required 4 amplitudes. Amplitudes. These are 4 complex amplitudes, complex numbers. A 3-qubit state requires 8 complex numbers. And a n-qubit state requires 2 to the n amplitudes. And so what happens here is, if a classical computer is trying to simulate all of the amplitudes and what's happening using the linear algebra, you're going to get this exponential blow up, and classical computers can't handle it. Whereas quantum computers, they're merely going on their way because they're practically doing the same thing that the real world is doing. So physical simulation is one of the reasons that quantum computers even came into existence. David Deutsch, who initially, I think he was the first person who proposed quantum computing, though someone could correct me on that. It's got a C in there. David Deutsch, he came up with the idea of quantum computing because he wanted to simulate physics. Yeah. So what else is it faster than classical at? Some other candidates are unstructured search. You may have heard of this. This is Grover's algorithm. Love Grover. We love Grover. His first name is Love. Grover's algorithm. So what this means is, if you have an array with n different objects in it, it'll say like x1, x2, ... xn, and you want to search for a specific object, but these aren't sorted at all. Classically, can anyone tell me how many steps this would take?
O of n.
O of n, yeah. So this would take O of n steps, because if you haven't found it by the n-1 spot, well, maybe it's in the last one. You don't know. You have to check every single element. With Grover's algorithm, Grover's search, you only need to do, you only need to do O of square root of n checks. You only need to look at O of square root of n different elements. This is a really surprising thing. If this makes no sense to you, that's one of the things that makes people interested in quantum computing. The catch here is that Grover's search relies on something called QRAM. It's the idea that you can have memory that can be in superposition, and we're not sure whether that's realizable. We don't know if it's possible to actually implement Grover's algorithm yet, but people think it is, and so that's why everyone's rushing to do things with quantum computing. And then another one is factoring, or actually more generally, it's period finding, which can be used to do factoring. And this is Shor's algorithm, which is probably the most famous of all quantum algorithms. And this, what it does, period finding finds the period in a function, but factoring is what you guys are probably more familiar with. It takes some number that's the product of 2 primes, let's say, and it tells you what P and Q are, the 2 primes that it. And so this would break modern cryptography. So in classical computing, this is in NP. But in quantum computing, you can actually do this in O of 1. Actually, it's a constant time algorithm, which is what the hell? That's shocking. Yeah, so there's a lot of promise going on here. This is O of 1 queries. I think if you actually do the math, it's not quite O of 1. I'm forgetting here. Yeah, so don't quote me on that. But yeah, Shor's algorithm, much faster than the classical algorithm. So these two generated a lot of excitement. And then yeah, so I think all of the current, I can't make that claim, it's not all of them, but a lot of the current quantum supremacy experiments, they rely on sort of physical simulation. They come up with like toy problems that would be very hard for a classical computer to mimic, and then they do it with a quantum computer and they get like a very, very small speed up, but they show that that small speed up is statistically significant. So that's what most of these quantum supremacy experiments are. Yeah, are there any others you guys can think of? I don't know. It's pretty good. Any other questions or any questions about these? Any questions about previous stuff we talked about? We're running into the 10 minutes left mark, so this would be a good time to start a small new topic if you guys are interested. What is quantum computer useful for? Looks like I didn't put that in grammatical error.
Do you think quantum computing is going to be a part of our job as a software engineer in the future?
If you decide to go into quantum computing, absolutely. If you don't, I personally doubt that it will be relevant for the average software developer in our lifetimes. But I think it'll be useful eventually. I think it'll be most useful for people in biology and chemistry eventually. I think it'll be, or perhaps if these quantum machine learning algorithms work out well, maybe everyone will be using it because machine learning has applications everywhere. But this physical simulation thing, like biologists and chemistry majors might be able to find new drugs quicker, might be able to like test certain treatments without actually having clinical trials, things like that. Yeah, but I doubt it'll get there within our lifetimes. Who knows? I'd be happy to be proven wrong. Any other questions?
Are most of like the issues right now mainly with designing algorithms or with creating quantum computers with more qubits?
It's definitely the latter, though it's not quite, I guess more qubits is accurate in a way, but it's really more fault tolerant qubits. It's not about how many, but how good they are. And something that we currently have, the buzzword is like NISQ, which is near-term intermediate scale quantum computers. And that just means where we get error correction to a level where you can actually use the computer even though it's super buggy. So like the main issue that's going on right now is like decoherence. Decoherence is where superposition collapses when you don't want it to, and so that can fall apart. There's also lots of different types of errors. Commonly, they split them up into X and Z errors. You can think of these like bit flips and phase flips. Yeah, and so all these errors add up. Right now, quantum computers, if you scale them, each individual qubit has such a big error that it just instantly, tons of qubits just become completely unreliable. So making these qubits, so I guess 2 bullets, making qubits more fault tolerant plus Also making error correction codes. Oh, making I'll write it out. Error correction codes, making better quantum error correction codes. So one code, just to give an example of what an error correction code is, classically, one common error correcting code in classical computing is the repetition code, where for every 0, you store it using like 3 bits, 0, 0, 0, and for every 1, you store it using 3 bits. And then if one of these bits magically flipped and it accidentally became a 0, 0, 1, well, you could compare the 3 bits. Oh, there's 2 zeros. So you take the majority and then you fix any bits that were mistaken. So what this does is it protects you from a single bit flip. And if you wanted to be protected from more, you could add more repetitions. Right? And you keep adding lots of them. There's much more clever error correcting codes than that, and there's quantum ones as well. And so coming up with new quantum error correcting codes that have really good specifications, that's a really broad open field. Lots of people are doing research on that. John Wright, who's one of our faculty, I think worked on that or is interested in working in that. But yeah. That gets really hard. There's like topological quantum error correction with using some really fancy math. I don't know. Any other questions? Any questions about how to use Qiskit? We got 5 minutes. Cool, cool, cool. All right, what did you guys, just some feedback. Any thoughts on these 2 workshops? Anything you'd like to see coming up in the hackathon? Any, what are you guys most excited for? We can just go. Oh, you can't hear me?
Oh, no, sorry.
Oh, okay, so he's on off mute. No worries, no worries. Yeah.
Yeah, so at the hackathon, what are we going to be doing?
Is the, I'm sorry, I can't hear him.
I'm sorry, I'm next to him. His microphone isn't working. He's
Yeah,
asking, during the hackathon, what it will be, like, what is an example of something that we're going to be creating or working on?
Right, yeah. So we'll go over it in the opening ceremony, but I'm gonna definitely spend a little minute to talk about that. So the idea that we want is that you should create, so the theme of the whole hackathon is education. What we mean by that is we want you to take some topic in quantum computing or physics. We want you to understand it, read up about it, learn about it over the course of the days. And then we want you to build something using IBM's Qiskit platform to teach others about that idea. That's the theme of the hackathon, the challenge of the hackathon. So all of you guys are going to be, I'm giving you a bit of a head start, I guess. All of you guys are going to be working on a project where you build something with Qiskit. And you're also going to have to record a 5 to 10 minute presentation explaining what you did. And you're going to put all of your files in a GitHub repository where the README explains what you did. We'll send out some more materials on that as well. But so the main things you're going to submit are a GitHub repo, and that GitHub is going to contain your code in Qiskit. It can use other languages too. It's going to include a README. That's important. It's going to be your document where you explain everything, and it's going to include your presentation. And then, yeah, and so theme, education. Yeah, any questions about that?
I have a question. Do you know what is the judging criteria? Because we're going to be ranked, I think. Do you know what's...
Yes. Yeah, I do know what the judging criteria is. It's pretty general. It's, what were the 4 things? Just don't quote me on this. You'll see it in the presentation tomorrow. One of them is complexity, like how interesting it is. I don't like the word complexity. Really, the way we're going to be judging it is not how complicated you make it, but rather how clear you're able to make it. So I would say clarity. But you know, the idea is that you have knowledge. The other one is it also started with a C. What was it? Oh, creativity. creativity, of course. Creativity. There was how well you use Qiskit. Although I'm not sure if we're still including that. The judging criteria, by the way, we're still working on it. How well you use Qiskit, and presentation. How well everything's done. So yeah, if you'll notice, I mean, creativity and presentation don't rely as much on knowledge of quantum computing. So even if you're a novice, you still have a really good shot at winning. So yeah, any other questions? We're right about hitting the hour. I might stay on another 5 minutes after the recording in case there's any questions you guys have that you couldn't ask because you were afraid because there was a recording going. But then after that, I'll say ta-ta, bye-bye. All right, well, I'll end the recording. Thank you guys all for coming. I hope this was helpful. Please give feedback on this in the general chats in Discord, anything else you want to see. And I'm gonna, how do you stop recording? Stop share, stop recording.